Canari is a library for online change point detection in time series. So the main architect behind the library is Van Dai Vuong. He was mentored by Luong Ha Nguyen and supported by Zhan Wenxin and David Warden. So what is Canari? So Canari, in terms of methodology, it's at the intersection between state-space model and Bayesian neural network using LSTM architecture. So what is it for? It is for online change point detection in time series. So you have an example here of data set with over multiple years where we can see that there are change points. So what we want to do is to be able to detect those change points online, meaning as data is received. So we see here in the green part, we have the training set that is used to train our time series model. We have in orange or validation set used to calibrate hyperparameters. And finally, everything that you see in red here is the result as you would see it if you would interpret the data online, meaning as data is coming. And what you can see here in blue is the probability of regime change or change point detection, which coincide with those regime changes that we can see in the raw time series. So not only it allowed to detect those change point online, it also allowed to decompose the time series into interpretable baseline, representing the irreversible effect in the time series as outlined in blue here, but also the rate of change. So we see here it was positive, switching to negative domain goes back in positive, and also the pattern. So the baselines are modeled by the state space model component, and the patterns, such as the one outlined in the third row here, represents the reversible effect that are those modeled by the LSTM Bayesian neural network. So in this case, we use a single time series, but as I'm going to describe later on, we can also rely on nonlinear dependency with respect to explanatory variable. And finally, in our decomposition, we also have access to a residual, the part that's neither explained by the irreversible behavior modeled by the baseline, nor by the reversible behavior modeled by the LSTM Bayesian neural network. So Canari has this unique feature of combining in a single holistic framework, state space model and Bayesian neural network, all of this building on analytically tractable Gaussian inference. Uh, Another task that it can do is it can also forecast because our change point detection rely on one step ahead forecast. By chaining these one step ahead forecasts, we can do short, medium, and long-term probabilistic forecasting. And we can do it, as I mentioned, also using nonlinear dependency with respect to explanatory time series or variable. For instance, if we have here a target time series and we have other input time series which can act as explanatory variable, we can build nonlinear dependencies using that Bayesian neural network that we use to model reversible patterns. So what are the building blocks of Canari? Okay, we build our time series model by combining together different components. So our first type of components are those associated with the baseline, the irreversible effect. So the first block would be a local level to model things that are constant for which the level might be unknown. The second one would be local trend for modeling things with constant speed, where that speed might be unknown, needs to be inferred probabilistically from the data. We could have a local acceleration, constant acceleration model to model things that will drift quadratically. In order to model either periodic or recurrent pattern, the first component is going to be a simple Fourier form periodic pattern to model harmonic responses. For more complex signal, this is where Canari distinguished itself by integrating a Bayesian LSTM neural network architecture in order to model both either periodic or recurrent pattern, as well as being able to model nonlinear dependency with respect to explanatory variable. And all of this is integrated seamlessly in the Canari library. In terms of residual, the blocks we have are either a simple white noise, so to model independent analytically distributed residual term over time, or more advanced ones, such as autoregressive residual term. And here we have several variants of it. So either a plain autoregressive term where you need to specify the parameter, or the more advanced one where it can perform Bayesian inference to self-estimate its own parameter, whether it is the autoregression coefficient or the process error associated with the residual. So all of this can be done seamlessly within the Canari library. And the nice thing with state space model is that we can mix and match any of those building blocks in order to create a model that would suit the need of your problem. So what is the go-to architecture if we want to do change point or anomaly detection? So we're going to start with a building block, say a local trend to model something with a constant speed. Then we're going to have something to model the reversible pattern. In this case, we're going to choose a neural network. And we're going to have a residual term. We're going to choose a simple white noise. So what we're going to do is that we're going to instantiate any of those blocks. So local trend, pattern, and residual. And we're going to be able to build our model by simply calling these tree blocks into our model class. So in this case, for the LSM neural network, we might have some parameters, such as the look back window, for which is going to build autoregressive dependencies with respect to the past. So if we don't know the size of that window that would be optimal, we can pass it as an hyperparameter that will be later on optimized. We can say how many features, such as hour of the day of the week is going to use, how many LSTM layers we want to use, in this case one, and what is the size of the hidden and cell state in my neural net, in this case 50. So all of these could be passed as parameter if needed. In this case, it's only the look back window. In the case of the white noise, I decided to use one where it's a simple one, and that parameter is also going to be passed as an argument, which later on will be optimized using the external RayTune library if needed. So this is a very simple component. In more advanced configuration, we can use, again, more advanced component that will enable to get rid of that tuning necessity by relying on closed form analytical inference in order to infer the parameters, such as here the process noise associated with our residual component. This is available in an online AR component. So if you want to get started, how to understand the method behind Canari and how to use the library. So all of this is available in our documentation, whether it is about the methodological background, how to install our library, how to read and pre-process data, how can we perform forecasts, how can we perform forecasts with dependencies, performing change point or anomaly detection, and finally, how can I tune the parameter of the model based on real data. So all these things are available in our documentation page. The link is in the video description. So you have here a little getting started on what is Canari, how does it work, as well as references associated with all the methodological development. If you want to know more about the theory, you can go here. You're going to have a complete list of references, either through books, papers, or video tutorial about background with respect to linear algebra, probability theory, probability distribution. Then all the theory about state space model, so Kalman filtering, smoothing, regime switching. Then we can describe here all the basic component, the theory behind it is available in those links. We can have here the reference as well for more advanced component, whether it is online autoregressive, the Gaussian multiplicative approximation, the approximate Gaussian variance inference in order to be able to do Bayesian inference for the process noise error estimation, or the bounded autoregressive component that can help in making more accurate change point detection in the case of drifting component. All of these are more advanced feature. Then, if you want to know more about how can we seamlessly integrate state space model and Bayesian neural network, look at this section here with TGI, where you can see how the tractable approximate Gaussian inference works and how does it enable to couple these recurrent neural networks with state space model. So all of this is described in those references. Then if you want to install the library, all the documentation is there in order to both install it from PyPy or install it locally from GitHub. Then we also created several tutorials in order to do things such as univariate forecasting, either using or not using LSTM. We can do forecasting using nonlinear dependency with respect to explanatory variable. We can do anomaly detection using that switching Kalman filter. And we can show how can we calibrate the parameter using synthetic anomaly generation. And finally, how to read data files. So all of this in the Canari library has been designed and developed by our research group, and we're going to keep maintaining and developing on that foundation by adding new features over the coming months and years.